Okay, hi everyone, and welcome to ISB 2021 oral session number 7 on sensors. Thank you for joining us today. I'm Dr. Crystal Kane, and I'm delighted to be chairing this session. Our speakers today are Lorenzo Room, Rhiannon Campbell, Guido Masha, Jasper Wong, and Stefano Di Paolo. As per previous sessions, our speakers will present for 10 minutes, followed by a short question period. And as a reminder, the audience will remain muted throughout the session. However, I encourage you to ask your questions as we are going along through the chat function. And then at the end of the presentation, I'll relay them to the speaker. Okay, so we're ready to kick off with our first speaker. And we have Lorenzo Room, who will be presenting his research on inertial sensor-based methods for phase and event identification in para rowers. So Lorenzo, when you're ready, you can share screen and I'll hand over to you.
Okay. Can you see my screen?
Yes.
Right now. Okay, perfect. Yeah, thank you for introduction and thank you all for being here, attending this this oral session this morning or evening or whatever time you are. So I'm going to start my presentation with a little background on para rowing. So para rowing is a Paralympic sport which was for the first time introduced at the Paralympic Games in 2008 at the Beijing edition. And the competition involves races that cover 2,000-meter distances on flat water and with different boat lengths and crew sizes. And para rowing, like many other Paralympic sports, do have its own classification system, which is basically based and it depends on the athlete's functional level, and for instance, whether he or she has or not the ability to control motion of trunk and or the legs. As an adapted version of rowing, para rowing shares with the main sport some similarities and differences. Among the similarities, we can find that on-boat or ergometer propulsion is obtained through a consecutive execution of stroke cycles, which each cycle can be divided into a recovery phase and a drive phase. The recovery phase begins at the finish start position, where the legs and back are fully extended, the arms are flexed and adducted tight to the body, and continues as the rower slides forward until reaching the catch position. From this point, the drive phase begins and the rower applies a pushing force to pull the handle backwards until reaching again the finish or start position. From the rowing literature, some temporal parameters of the stroke cycle have been identified as indicators of performance. Among them, we can find the stroke rate, which is basically the number of strokes per minute, and the drive and recovery phase durations, as well as the drive to recovery ratio, which is a parameter that is usually used to describe the athlete's rhythm. Among the differences, first we find the equipment modification, which is the equipment is adapted to allow the athlete to perform the rowing technique. So we can find on the boat or on the ergometer the presence of boat seats or leg or trunk straps. So according to the athlete functional level, we can find some different rowing setups and technique, both on boat and on ergometer. The first one, which involves the use of leg straps and includes the athletes that have the motor control of trunk and arms, and they use these body segments in order to propel the boat. And the second setup, which use both leg straps and trunk straps plus a boat seat, in which the athletes use both arms and shoulder in order to propel the boat. As can be imagined, these two different techniques entail some peculiar differences in terms of joint kinematics compared to the usual rowing technique, which allows the normal leg motion. which so far have been only investigated by Cutler and colleagues in a laboratory context, using an indoor rowing machine and testing only non-disabled athletes. So therefore, from the literature, but also from today's sports practice, there is a need from a shift or a transfer from indoor to outdoor context in order to quantify the performance, the sports performance. And in this case, wearable sensors such as inertial measurement units are playing an important role. For what concerns the use of inertial sensor or IMU for rowing performance assessment, a very recent systematic review analyzed this issue. And among the included papers, 67% of them, they were about the monitoring of stroke quality, investigating the stroke rate, the stroke variability, and the phases ratios. However, the sensor positioning for the stroke phases definition, the recovery, and the drive phase was mainly on the oars or on the handle, whereas none of the included study reported a positioning directly on the body of the athletes, which leads to somehow quite a problem or misuse of these sensors, because we are not, or in the literature there is no use for this sensor to compute or to obtain joint kinematics while still analyzing the stroke quality. And needless to say, there is no available literature on athletes with disability, unfortunately. To this end, the purpose of our study was to propose and validate a methodology for the segmentation of the stroke cycle through the use of wearable sensors for athletes with disability. As a preliminary study, we tested one non-disabled experienced rower, which performed the rowing technique on an indoor rowing machine, which was equipped with a fixed seat and a set of belts depending on the para-rowing setup. The experimental protocol involved an initial part of warming up, plus 3 minutes trial at a fixed stroke rate of 36 strokes per minute for the two para-rowing setups. So the one which involved the use of leg straps, and therefore the rowing technique, which was basically based on trunking arms, and a second para-rowing setups, which involved the use of both straps and seat, and therefore entailing the arms plus shoulder rowing technique. A motion capture system was used to identify the catch and finishing time distance from the right-hand wrist marker trajectory, and in particular from the axis with was longitudinal to the rowing machine main axis. 3 IMUs were used and positioned on the forearm, upper arm, and a trunk level at T9 level. From the data acquired from the IMUs, 6 algorithms were implemented for the identification of both catch and finish events, in particular from the accelerometer and gyroscope data. Here, just for representative purposes, you can see the signals from the accelerometer and the gyroscopes for the 2 conditions or the 2 para-rowing setups and the 3 sensor placements. And here, I don't know if you can see also, there are some icons for catch and finish distance. And on the right, just for reference, there are the 6 algorithms that were implemented in order to identify the 2 events from the IMU's data. To evaluate algorithm accuracy, visual inspection for wrong identification, that is missing or extra events, was performed, plus time difference in finish and catch event detection between the motion capture system and the IMU's data were computed. For what concerned the results about errors in event identification, the sensor placement at forearm and upper arm led to 0% of missing or extra event, whereas the trunk positioning led to a 4% of missing and 2% of extra events. For algorithm accuracy, similar results were shown for the two positioning at forearm and upper arm, with the finish event being the most accurate event being identified. And here on the right, you can see in the table the delay between the iNews data and the motion capture data in the two conditions. The catch event was early detected in both power-rowing setups, whereas the trunk positioning lead to less accurate results. In particular, delayed detection of most events were recognized, plus a greater variability in the finish position detection was observed. Discussing these results, the proposed methodology showed a level of accuracy that ranged from 8 to 69 milliseconds, which can be considered as acceptable for most para-rowing contexts. In fact, if we look at the latest results in para-rowing during the last Paralympic competition, the level of accuracy measuring the total race time, which is the main performance outcome in this sport, is of a sense of the second, and still differences between a gold and silver medal are even of about few seconds. For what concerned the accuracy related to the sensor placement, the upper link placements led to a more accurate detection of stroke events with respect to the trunk location. This was because the signals from these two positioning location displayed a more regular repeatable behavior with easily detectable feature of the signal, whereas the trunk acceleration and angular velocity proved to be less suitable for detecting the catch and finish events, because the movement of this segment, the trunk segment, is altered due to the equipment setup. So the straps for thigh, pelvis, and the thoracic straps, or the presence of the boat seats, and therefore by the stroke technique itself, basically. So these results suggest that para-rowing technique and para-rowing setup should be taken into account when selecting the sensor placement if the aim is the temporal segmentation of the stroke cycle, because the accelerometer signal or the inertial measurements from these body segments present some technique-specific features. For future directions, of course, we are aiming to apply these methodology to para-rowers that use the different para-rowing setups, and increase, of course, the sample size to introduce some serious statistical analysis. But also, we want to exploit the full potential of wearable sensors through the simultaneous computation of joint kinematics, in order to move finally on board and being very useful for coaches and trainers they are quite in need of this kind of instrumentation in these sports. Thank you for your attention.
Thanks, Lorenzo. If anyone has any questions, just please type them in the chat. I'll just ask a quick one. Is there anything that you could think of that might actually improve the identification of that catch, even though the timing is still acceptable? Is there ways that we could make it a little bit more accurate?
Yeah, the way that to make it more accurate would be to place the sensor on the oars on the handle, but still in that way there is the limitation that we cannot exploit the full potential of the sensors. Once we get a very good model in estimating the joint kinematics of the upper limb, because for the trunk it's quite easy, whereas for the upper limb joint kinematics it's more difficult, the thing. But yeah, the solution would be positioning the sensor on the handle or on the oars, which is an indirect way to measure the performance. So instrumenting the equipment, but still doing so, we will limit ourselves. from my point of view, we are limiting ourselves to the equipment and not observing what the athlete is actually doing in the meantime, of course.
Great. Thank you very much. If there's anyone has any follow-up questions for Lorenzo, then please feel free to put them in the chat. And Lorenzo, if you could just respond there, that would be great. We will move on to our second speaker. We have Rhiannon Campbell, who is presenting on forearm loading and symmetry during artistic gymnastics vault training sessions. So Rhiannon, you're getting the slides ready, which is perfect. And whenever you are ready.
Wonderful. All righty. Can everyone hear me?
Yes, we're all good.
Good. Thank you for coming today to watch this presentation, which is titled Forearm Loading and Symmetry During Artistic Gymnastics Vault Training Sessions. So vault is an apparatus that both male and female gymnasts perform in competition. It involves the gymnast sprinting down a runway, jumping onto a board, launching themselves up onto the vault, and then pushing off from their hands to perform multiple acrobatic maneuvers prior to landing. In order to achieve a successful vault, a quick and forceful push-off from the arms is needed to increase the height and distance of that flight phase, and this allows gymnasts to perform more twists and somersaults prior to landing, which increases the difficulty and the overall score of the vault. But this does place the upper limbs under considerable loads, which has raised injury risk concerns. So we know from previous research that repetitive high magnitude loading of the upper limbs is a major extrinsic risk factor for injury, particularly during the growth and developmental years of young gymnasts. Asymmetrical loading between the upper limbs can also increase the risk for overuse injuries, particularly if one limb is consistently exposed to a higher level of loading. And this is really important in gymnastics because gymnasts will often train their skills using their preferred or leading limb only in order to achieve that performance consistency. So some vaults have been associated with wrist pain in gymnasts. So for example, we've got Sukahara vaults. During the vault contact, the wrist hyperextends and moves into ulnar deviation and is obviously associated with wrist pain. So for this reason, the primary aim of this study was to investigate the magnitude and symmetry of forearm segmental loading when performing foundation to advanced level vaults within a training session. So 6 female and 6 male elite level gymnasts agreed to participate in this study, and IMUs were placed bilaterally at the third and distal quarters of the forearms, and these were attached using double-sided tape and fixed mole. So here's some footage from the data collection sessions. Data collection took place in each gymnast's own training center and during their usual training sessions. So we didn't actually ask the gymnasts to perform any specific skills. They just did their usual program as per their coach instructions, and we just recorded whatever skills they did in that session. The IMU data was collected simultaneously using an iPad and the iMeasureU research application, and we also got some video footage of the sessions as well. So peak resultant forearm acceleration during all hand contacts were exported, and these were grouped into either the lead or the non-leading forearm. And this was done to account for individual preference between the gymnasts, because some of the vaults, they twist in them and one arm will contact the vault before the other. A symmetry index score was calculated for every hand contact that occurred between the leading and the non-lead forearm. Now, clinical definitions of functional imbalance aren't well established in gymnastics, but it's generally accepted that a symmetry index greater than 10% may place a gymnast at a higher risk for injury. For our statistics, we decided to use non-parametric descriptive statistics because we didn't want to collapse all the data into a single mean for each gymnast or vault in order to maintain that individual variability between performance. So that's why we went with non-parametric descriptive statistics. Now I'm going to start with the female vault results today. So all females performed Yurchenko entry vaults. Now, during a Yurchenko entry, the gymnast does a round off, landing on the springboard, and then proceeds to contact the vault from a backward entry position. Now, there are two hand contacts that occur during a Yurchenko vault. We've got the first one in the round off entry, and then the second one is during that vault contact. So both of them were analysed in this study. So we've got the median and the interquartile ranges plotted here for all of the hand contacts and the symmetry index down below. Now the striped bars are the round off entry hand contact and the solid bars are the vault contact that occurred. So during the entry and the vault contact for the Yurchenko tuck and the vault contact for the Yurchenko pike, we saw significant asymmetries between limbs. Now, this is a particularly interesting finding as the vault contact during the Yurchenko vault appears symmetrical in nature, whereby both hands contact the vault at the same time and they push off using a very similar motion. But as you can see, these results indicate that even though the movement appears symmetrical, the loading experienced can still be asymmetrical. So moving on to the male vault results. Now, the males performed two different types of entry vaults. So we've got handsprings and Sukahara. We'll start with the handsprings here. So during a handspring vault, a gymnast will take off from the springboard and contact the vault in a forward entry position. Now, in a handspring vault, there's only one hand contact that occurs, so we're only analysed that one hand contact. So here's our results again. We've got the front handspring, the front pike, and the Dragulescu vaults showed the leading limb experiencing a higher level of loading, whereas the handspring front tuck, it was the non-lead forearm that was experiencing that greater load. Now, similar to the Yurchenko here, handspring style vaults also have a contact phase that appears symmetrical, but once again, we did see asymmetrical loading present. And finally, the Sukahara entry vaults. So during a Sukahara, a gymnast will take off from the springboard and proceed towards the vault in a forward entry position, but they will perform a half turn prior to contacting the vault. So there's a 180-degree turn before hitting the vault. There's only one hand contact phase that occurs here as well, so only one's analysed. So during the Sukahara tuck, the Sukahara layout full twist, and a Kazamatsu full twist, we did see asymmetries present again. Now, there were some trends that emerged between these different vaults here. So generally, when the gymnast was performing a Sukahara vault, it was the non-lead forearm that was experiencing that higher loading. And then for the Kazamatsu, it was actually the lead forearm that was experiencing that loading. Now, these may be due to the technical differences between these two different vaults, and I'll try my best to explain them. So both these vaults have the same entry phase. So they both do that half turn from the springboard onto the vault, but they do differ in the flight phase. So in a Sukahara vault, a gymnast will rotate in one direction from the springboard to the vault, and then will change the direction that they're rotating in the flight phase. In a Kazamatsu vault, they will maintain their twisting direction from the springboard to the vault and then continue in the same direction in the flight phase. So during these two vaults, the gymnast will have to change which arm they push off in order to change their twisting direction, and that might explain why we're seeing these different loading trends between these two vaults. So in conclusion, IMUs can be used within a gymnastics training environment to provide a proxy measure of limb loading and symmetry. Advanced level artistic gymnasts experience forearm loading asymmetries when performing some Yurchenko, handspring, and Sukahara entry style vaults. The vault contact for the Yurchenko and the handspring vaults do involve both hands simultaneously contacting and pushing off the vault, However, the loading experienced in this study was still asymmetrical. And this just highlights that even during symmetrical gymnastic skills, one limb could still be experiencing that higher loading, which is not likely detectable through visual observation. Thanks.
Great, Rhiannon. Any questions from anyone in the audience? Please feel free to share them in the chat. While we're waiting, and I know very little about gymnastics, I'll admit that. So that's very interesting, I found. For the vaults where both hands were in contact with the vault, are they in contact parallel with one another or are they staggered? And then how did you, I guess, identify the lead in that if they are at the same level, which one considered the lead?
That's actually a really good question. So in the handspring and the Yuchenko vaults, where I said that they looked symmetrical, their hands should be parallel, but variations, sometimes they might be slightly off. The way we defined the leading forearm in that was, so with the Yuchenko still, they do a round off. So they'll take off with one leg and one hand will contact the floor before. So that is their sort of leading limb in that situation. And that's how we defined the leading limb, is we got the gymnasts to do cartwheels or a round off, and then the arm that contacted the ground first was considered their leading limb.
Great, thank you for that.
No worries.
That makes complete sense for me. So just a few questions. So Helen Bain has asked, interesting that the Yurchenko layout had lower symmetry on the vault table than tuck or pike. Any thoughts on why?
I thought that was interesting as well. We did have a relatively small sample size, so it could maybe be that the level of the gymnasts as well that perform those vaults. So like the Yuchenko tuck is the easiest of those skills, and the Yuchenko layout is much harder. So potentially the gymnasts that were performing the layout were a bit more experienced with these skills, and maybe that's why they were a bit more symmetrical in their contact phase, but I'm only guessing.
Great, thank you. And just one more question before we move on. There are a couple in the chat, so I'll leave the other ones for you to answer. But one from Valentina sorry, Valentina, I'm going to pronounce your name wrong. Camomilla. Good to be able to protect athletes from injuries. How sensitive are your parameters to sensor limitations and fixing?
Yeah, that's something that we definitely would probably need to look further into. This was one of our sort of very early on pilot studies. So that definitely needs to be looked into further before we sort of implement this. Yeah.
More athletes. Thank you for that, Rhiannon. We'll now move on to our third speaker, and we have Guido Masha, who is presenting on an automated method for estimating vertical jump power through inertial measurement units. So Guido, when you're ready, we'll get Rhiannon to stop share. And then there we go, we should be able to switch over.
Can you see my screen correctly?
Yes, we've got you now.
Okay. So thanks for the kind introduction, and my work will focus on vertical jumps and power generated from them. In particular, vertical jump is a motor task which is often utilized for assessing the neuromuscular capacity of an individual, in particular generating mechanical power at lower limb level. Both the concentric and, when available, also the eccentric part of it. To this purpose, counter movement jumps and squat jumps are tests that are used to stress for lower limb power generation ability. And in particular, peak and mean concentric power during the propulsion phase are of particular interest. Moreover, the mechanical power is complementary to the estimate of jump height during this task. The instantaneous mechanical power and also the height can be computed easily through a force platform, which represents the gold standard for such kind of measures. However, inertial measurement units, or IMUs for short, can overcome some of the force platform limitations, such as costs or limited portability. But still, other issues are present, mainly in the form of inertial effects, wobbling masses in a wider phenomenon known as the soft tissue artifacts. The soft tissue artifact, or STA for short, cannot be removed with any digital filtering technique, since it is both task and subject dependent. And computing directly the jump height during the jump height directly from IMU measures and acceleration is affected mostly by wobbling masses inertial effect. Indeed, as you can see from the right-hand side picture, there is no such a possibility. It is virtually impossible to distinguish both the takeoff and the landing time instants. However, peak power occurs prior to the actual takeoff time instant. Hence, we hypothesize that it is less affected by soft tissue artifact. So, the aim of the study was, at first, to reliably assess the peak and mean concentric power using IMU recorded data. Then to include both anthropometric and time frequency features, which we thought to be potentially related to STA in order to improve the IMU-based estimates of power parameters, hence devising multiple linear regression models. The experimental setup involved 17 healthy participants, which performed 3 CMJs and 3 SJs each on a force platform, wearing a belt provided with an IMU. And we chosen to the elbow to be brought at waist height in order to minimize the arm swing effect. But such non-conventional setup was due to the fact that we used this setup to record also smartphone data for another study, which involved a similar approach in an attempt to democratize such kind of process. And moreover, 4 skin fold lengths were measured, namely biceps, triceps, subscapular, and iliac crest, and power measures were normalized to each participant body mass in order to allow for a comparison between instrumentations. Then, aside from the aforementioned skin fold, which represented the anthropometric features, other features were also included. In particular, at first, peak and mean concentric power computed through IMU, as well as, when available, the peak and mean eccentric component of the same. And moreover, a P delta value, meaning the time interval between peaks in case of CMJ, or between the start and the end of the concentric phase, the peak of the concentric phase for the squat jumps. And moreover, 3 other time frequency features were extracted through variational mode decomposition as the central frequencies. The F3 low frequency component was associated with the jump, whereas the mid and high frequencies, F2 and F1 respectively, were associated with the wobbling inertial effects. Then we computed peak and mean concentric power through the gold standard measures. We combined the aforementioned features in multiple linear regressive model in order to compute corrected estimates with respect to the IMU estimates. Then, to select the best subset of feature, we used the best subset regression method, and to validate model, a tenfold cross-validation approach was used. And the best model was chosen to be the one with the lowest cross-validation error. Moreover, to have an overall quality metric versus the FP values, we used the mean absolute error. In this table, the beta standardized coefficients for each of the 4 regressive models are shown. It's easy to see that power-related features appear appearing basically all the best subset automatically selected, and the scheme folds do the same. Interestingly, the high central frequency component computed through the VMD, variational mode decomposition, appears only in squat jumps. Here are the regression results for the concentric peak power analysis for CMJ in blue and SJ in orange. And on the right-hand side, the mean absolute errors are showed, along with the percentage for each error method showed versus the actual overall value of the force platform. The CMJ regression improved the estimates in terms of error of about the 10% with respect to the error brought by the IMUs alone. And for SJ regression, the IMU estimate was improved through MLR of about the 5%. Accordingly, these are the regressive model results for mean concentric power. And interestingly, the overall best model was obtained for counter movement jumps in this case scenario, diminishing the error of about 15% down to 6% with respect to the overall value of the force platform data. Finally, even with lesser extent, the SJ regressive model for such variable improved the IMU estimates too, lowering the error of about 5%. So finally, in general, all the regressive models, we can say that reduce the estimate errors in terms of mean absolute errors. The squat jumps related ones presented slightly higher errors, possibly suffering from a lower number of available features since there was no eccentric power component in it. Moreover, CMJ's multiple linear regression performed better, embedding anthropometric parameters, possibly due to inertial effects brought by wobbling masses in terms of scheme folds, which were more impactful during the counter movement phase. And future studies should focus on elite athletes because we did not recruit elite athletes for a more robust generalization. And these kind of studies should be extended also to jump height estimate. Indeed, an attempt at democratization for jump height estimate, as I said, was attempted using a smartphone, and it was published in another proceeding for another conference by us. And you can find more of this and latter aforementioned study in the link following the QR code here on screen. Thanks for your attention.
Thank you, Guido. That was a great talk. If there's any questions from anyone, please, again, type them into the chat. I'll kick off with one. I actually found it a bit surprising that the squat jump didn't perform as or had greater error in, and I guess I was thinking because there would be less wobbling with them holding that squat position at the start and then moving versus a counter movement where they're going into that eccentric and coming up. And I noticed that in your squat jump, in the mean power graph, there were 3 athletes or 3 trials that were kind of grouped towards that right-hand side of the graph that seemed to perform quite differently to the other athletes. Did you have any comments on that and your thoughts on it?
Basically, as I said in the discussion section, we did not recruit really experienced jumpers, let's say. Indeed, the video I was showing of the person jumping, where it was me on that video, and I'm not an athlete. And I think that that part is the one which affect the estimate the most, because it's not so easy to a not experienced athlete, let's say, to to jump as a normal to select that jump as a good jump. I don't know how to say it, and I think that those could be outliers, but also due to errors in the IMU, which we wanted to correct for.
Yes, for sure. You try to get somebody that's inexperienced to hold that squat and just go vertical. It is very, very difficult to do.
Yeah,
definitely. Is there any questions from anyone in the audience for Guido? If not, I think we'll move on to our next speaker. If anyone does have any questions that they think of, then please type them into the chat and Guido can respond in there as well.
of course. Thank you.
Thank you. Okay, so our next speaker for this session is Jasper Wong, who will be presenting on real-time haptic feedback system validity and its feasibility for runners in real-world training environments. So Jasper, when you are ready, we'll hand over to you.
Cool, thanks, Crystal. Is the screen sharing okay?
Yes, we're all good, thanks.
Yeah, thanks everyone for being here. And also thanks to Kelly, Sharon, and Hannah White for part of this project as well. So just a bit of overall background. When it comes to running overuse injuries, there are a number of different potential risk factors, some of which include high tibial accelerations and high vertical force loading rates, which are both related to landing impact forces. So running mechanics or running technique is one factor that can contribute to the magnitude of these forces. So there are a number of different components of running technique that can be modified to reduce the impulse of landing. Two of these are step rate and the trunk inclination angle. So typically these are modified with the use of real-time feedback or cues. And the most common types of these feedback are a range of visual and audio feedback. However, these are generally limited to laboratory use. So haptic feedback or feedback through the sense of touch is also another potential strategy, but so far there is limited research on its applications. And again, these have been limited to a lab setting. So recently a company called Sage Motion developed a real-time haptic feedback system that could potentially be used outside of the lab. So the system comprises of these sensors, which are inertial measurements units integrated with haptic feedback capabilities. So these sensors connect via Bluetooth to a base station, which then stores the data. And the whole system is activated using a smartphone or tablet or computer. However, everything sort of needs to remain within a certain distance, otherwise the sensors will disconnect and stop recording. So at the time, the system was only able to measure step rate and trunk inclination angle. So they had looked at some validity stuff with walking and jumping activities, but so far they hadn't looked at any validity for running activities. So therefore, our aims for the study were to firstly assess the validity of the system in measuring step rate and trunk inclination angle during running. And then secondly, to assess its feasibility in modifying running technique in an outdoor environment. So before starting any data collection, we did a bit of pilot testing to determine the best location for the trunk sensor. Then in order to assess the system validity, we conducted a laboratory treadmill running assessment using the sensors, the 3D motion capture, and a force plate instrumented treadmill. And then following this, we conducted 3 outdoor training sessions to assess its use in the outdoors. So in total, we used 3 sensors. So the wrist sensor worn on the wrist provided the haptic feedback. So it would vibrate when the participant was not meeting the target threshold. We had a sensor on the lower back at the L2 level, which measured trunk inclination angle, and then one sensor on the shank to measure step rate. So for the study, we had 10 recreational runners, 5 male, 5 female. For the in-lab validity, we validated the haptic feedback system against current gold standard measures. So these were 3D motion capture for trunk inclination angle and a force plate instrumented treadmill for step rate. So participants were given a 5-minute warm-up at a self-selected pace, during which we collected baseline data. Based on these baselines, the participants do times where they either increase their trunk inclination angle with the use of the haptic feedback. So the targets for these, the target thresholds for these were a 10% increase in step rate and a 10-degree increase in trunk lean, which was based on previous literature. So following the lab session, we assessed the outdoor feasibility with 3 10-minute outdoor training sessions. Participants aim to increase their step rate using the haptic feedback based on their target threshold from the lab session. They ran at a self-selected comfortable pace, and they were paced by a research assistant on a scooter mounted with a GPS. We also asked them how they found the haptic feedback. So after the third session, participants completed one final lap with no haptic feedback or pacing to see if they could maintain the increased step rate. So onto the results. Here we've got a graph showing the differences in step rate measures between the sage motion system and the instrumented treadmill. So on the y-axis over here, we've got the difference in mean step rate per minute. And then on the x-axis, we've got the subject number. And so the black bars represent the baseline condition and the green bars represent the increased step rate condition. So although it does look like there were some large differences during some of the runs, the scale is actually quite small. So the actual difference between the two systems would have been anywhere between 0 to 2 steps per minute. So t-test showed that there were no significant differences. So we concluded that the sage motion system was valid within 1.1% of current gold standards for step rate measures. So for the trunk inclination angle, similar graph. So showing the differences between the sage motion system and 3D motion capture measures. So we've got difference in mean trunk angle on the y-axis and subject number on x-axis. And again, for both baseline and increased trunk lean conditions. So this time there were clearly large differences. As you can see, the scale is larger. And also this was more evident during the increased trunk lean run. However, t-tests again showed that there was no significant differences, which was quite interesting. And we think this was due to the large variability in the sage motion system measures. So to sort of get a picture of this, we can look at the real-time trunk angle during the increased trunk lean run. So we've got trunk lean angle on the y-axis and then time or frames measured on the x-axis. So we can see that although the participant starts off at this angle here, indicated by the yellow line, the measures from the sensor sort of drift over time and record a negative trunk angle or a backwards lean over time. And this was despite the participant running with the same amount of trunk lean throughout the whole period. So this is just another example, but going in the opposite direction, which would suggest that the participant kept leaning forward over the course of the run when in fact they didn't. So we can see here that there was notable drift in the sensors and at both over and underestimated trunk angle. So to illustrate this variability, we ended up doing a Bland-Altman plot, which measures the degree of agreement between two different methods of measurement. So here we've got the difference in trunk lean angle between the two systems on the y-axis, and then the mean difference in trunk lean angle, and the mean trunk lean angle on the x-axis. So the blue line in the middle represents the mean difference in trunk lean angle, and then the upper and bottom lines represent the limits of agreement, which is calculated as the mean difference plus or minus 2 standard deviations. So basically what this all shows is that usually when all the differences are within the limits of agreement, then the agreement between the two systems would be acceptable, or both of their measures are quite similar. However, in this case, we can see that the limits of agreement are very large, which suggests that trunk angle measures from the sage motion system can be anywhere between 96.4 degrees above or 87.4 degrees below what is measured by 3D motion capture, which in a clinical sense isn't very realistic. So we concluded that the sage motion system wasn't valid for measuring trunk angle. So onto the outdoor feasibility. Here we've got a graph showing the mean step rate per minute in the different sessions. So we've got mean step rate per minute on the y-axis and subject number on the x-axis. So the blue dots here represent their mean step rate during the baseline. And then the yellow, orange, and red dots represent their mean step rate per minute during their training sessions using the haptic feedback. And then these green dots represent their step rate per minute. And final black when we have no feedback or pay. So we can see here that we're able to increase their mean step rate after only 3 training sessions. And all participants found the haptic feedback quite intuitive to respond to as well. So in conclusion, we can see that the sage motion system was valid for measuring step rate, but not trunk angle during running. This was likely due to hardware or algorithm issues that need to be addressed by the company before future use. In terms of outdoor feasibility, the system is feasible modifying step rate in an outdoor environment. Some features would be actually assess the effects of a longer intervention on reducing tubular acceleration and or force loading rates in more target population. So I just want to take this opportunity to thank Sage Motion for providing the system to us at no charge for this study. And also thank you everyone for listening. If there's any further questions or comments, please feel free to reach out. Thanks.
Great job, Jasper. Very interesting study. And I think wearable is where a lot of things are going. And runners are a group that love to have data. So I think it's very interesting to look at those sensors. There is a question in the chat from Valentina. Did you test for retraining of step rate increase in any subsequent state sessions?
No, yeah, so it was quite a short pilot study from our side. It was just the initial testing, just where it was like feasible for modifying step rate in an outdoor environment. So that is definitely something that can be taken into consideration for future testing. Yeah.
Yeah, just to follow up on, I guess, that and looking at it in long-term use, you mentioned that the athlete could only be so far from the base station. How far away can you be in thinking about how runners would use this, I guess, if they are going on an actual run and not just on a track?
Yeah, I can't remember the exact distance, but it wasn't a lot. Like, we couldn't leave the computer or base station somewhere while they ran around on a 400-meter track. So basically the person pacing them on the scooter was carrying all the gear, which, you know, not very practical if you want the runner to be able to use the system by themselves. Like, they'd have to carry everything. So definitely a bit of streamlining to do with the sensors themselves, but sort of the implications of the haptic feedback being feasible was quite cool.
Yeah. And in terms of the trunk lean and that drift in the signal, is there any suggestions that you guys have provided back to the company maybe on how to improve their devices for that measure?
I think it was more of an algorithm thing, which we weren't too knowledgeable from our side to be able to offer much insight into that. Yeah, that's with the walking or jumping exercise that running actually brought about the errors. But yeah, I think that's something for them to figure out more of.
sorry, this is the third follow-up. Did you find the same thing with the trunk angle when you were on the outdoor running? Did you look at that at all?
Oh yeah, so we didn't look at it based on that lab part because it wasn't reliable at all, so we didn't end up using it.
Okay. Yeah, I was just wondering if there was any difference between just being on a treadmill running in a single spot versus potentially running around a track.
Yeah.
Okay, if there's no other questions from anyone, we'll move on to our last speaker. Thank you, Jasper. So we have Stefano Di Paolo, who's talking about typical risk patterns for ACL injury is largely present in competitive athletes, and looking at biomechanical screening through wearable sensors. So when you're ready, Stefano.
Everybody, can you see my screen?
Yes, we can see your screen and we can hear you as well. Thanks.
Okay, perfect. So, hi everybody. I'm Stefano Di Paolo. I'm a biomedical engineer and a PhD candidate at the Department for Life Quality Studies at University of Bologna and a collaborator for Rizzoli Orthopedic Institute, always in Bologna. And I thank you all in advance for listening. As we all know, anterior cruciate ligament injury is one of the most devastating injuries in sports, and it has devastating consequences for career, health system, and long-term fitness of athletes. High rates of anterior cruciate ligament injuries are found, and especially in the young population, young and competitive athletes, these rates are increasing. A recent study said that in female sports it's at least doubled in the last 10 years. So this burden is really becoming heavier also in young population. Another important aspect is that we have frequent re-injuries, and this might be due to the rush to return to sport without player readiness for the post-match injury conflict. And as we can see on the picture on the right, we have an Italian national team player which had 2 injuries at the age of 20 years old within 8 months, basically. And as you can see, there is a strong biomechanical role in this type of injuries. In fact, we have really predominance of non-contact ACL injuries, up to 90%, non-contact or indirect contact. So there is a crucial role of athletes' biomechanics. Recent studies also underline specific biomechanical patterns for anterior cruciate ligament injury, and differently from what it was seen in the past years, there is not just an involvement of the knee joint where the rupture actually happened, but it's multifactorial and multi-joint injury. So full body is interested. So one big open question in the field is, can we predict the primary ACL injury risk magnitude through an assessment of the player's motion, athlete's biomechanics? To go deeper into this question, we for sure need to start asking ourselves if this risk pattern is present in healthy population in general, and to what extent this happens, and if there are any associated factors, for example, if gender, movement complexity, and so on are associated factors to the risk patterns, biomechanical risk pattern for anterior cruciate ligament injury. So the aim of our study was to investigate the presence of biomechanical risk pattern for anterior cruciate ligament injury in healthy and competitive athletes population during the execution of high dynamic movement. We hypothesized a large presence of anterior cruciate ligament risk pattern in this population, and we also hypothesized the association of this risk pattern to female gender and movement speed. The cohort that we investigated was made by 34 subjects, equally distributed among male and females. They were all young, average age was 23 years old, and all belonging from pivoting sports, mainly football, soccer, with a Technical level 9. To conduct our biomechanical analysis, we use a set of wearable inertial sensors from Xsense. Particularly, we use a set of 15 inertial sensors, and we capture full body kinematics. The movement tasks that we investigated were a change of direction at 90 degrees and a frontal sprint with deceleration. Both movements are analyzed in a specialized laboratory equipped with artificial turf and are movement commonly found in pivoting sports. And also, as literature recently underlined, these are also two of the main situational patterns for anterior cruciate ligament injury. So to process our data, we decide to crop the ultimate strike before the change of direction in accordance with literature. So to reduce our kinematic analysis to a single strike, and in particular to two frames, which were the initial contact and the maximum knee flexion angle frame. This was also in line with recent literature. To define a movement for each athlete as at risk, we set up a set of 9 risk factors derived either from literature or from our data distribution. As in the picture you can see on the right, this is the main biomechanical pattern found in athletes who underwent anterior cruciate ligament injury. The 9 risk factors are the ones that you can see in the picture on the left, and they mainly belong from 4 different categories, which were foot position, trunk position, limited lower limb flexion angle, and dynamic knee valgus. To define a movement as at risk, we said that a minimum of 5 simultaneous risk factors need to be present to define this movement at risk. When we had specific pressure, quantitative pressure from literature, we used them. Where these thresholds were not available, we use our data distribution, and so we used the values that were out of the interquartile range to set up a value as at risk for each parameter. So the results regarding the rate of at-risk movement patterns, we found an overall high rate of movements. We collected 400 varied trials, which were 3 per leg per movement, and we had a risk pattern rate of from 9 to 12, which was similar between the change of direction and the deceleration tasks, and which was also similar between the initial contact and the maximum knee flexion angle. If we want to look more in detail and what happened to specific athletes, we saw that the at-risk pattern was present in at least one movement in the 71% of our cohort. So basically 1 out of 4, 3 out of 4. And that 15% of the cohort showed the risk pattern in at least 3 movements, up to 5, up to 12. We also conducted a multinomial logistic regression to investigate the associated outcomes, and we found that approaching speed was statistically significantly associated. So higher approaching speed was associated to higher rate of risk patterns, and that also female gender was associated with higher risk of risk pattern with odds ratio of 4.3 and 4.8 respectively. So in the discussion, we saw that the anterior cruciate ligament biomechanical risk pattern was really largely present, 1 out of 10, and that some athletes also showed this risk pattern multiple times. So we asked ourselves if there is in this competitive young population the need for large screening to investigate the presence of this potentially dangerous pattern for so devastating injury. We also found that faster movements means higher risk, and this is perfectly in line with literature regarding the injury performance conflict. But this makes also ask ourselves if on-field movement might be different from the in-lab ones, as soon as in-lab movements typically do not reflect all the conditions that you find in the pitch, and specifically the speed that player have to have. So we say that there is a need for dynamic testing in dedicated space, either indoor or outdoor. Then we also found a higher risk for females, and this confirms trends, especially for football female injury, which is rising as soon as the competitiveness level is rising too. But we also know from literature that female athletes benefits more from preventative training than they male players. So as take-home message, we say that large training in young population is needed toward these biomechanical risk patterns, and that when athletes with at-risk patterns are found, attention should be paid to them with preventative neuromuscular trainings. Then we also say that multitask batteries are needed to confirm if this pattern is just occasional or factual. So if this pattern happens just once, or if it's really something that happens often in a player's motion. Then we say that quick and effective biomechanical investigation in real environments are needed. For example, through the use of wearable sensors, as we did for our study, but also through the use of markerless technology, as soon as we have fast calibration, no space encumber, and fast data processing. So I want to thank my research group for this, and thank you all for your kind attention. And I welcome every question.
Thank you, Stefano, for your presentation. And I think ACL injuries is always something that's very topical, and looking at how we can try and get these measurements done outside of the laboratory to look at those movement patterns is something that's going to be progressing as we move forward. In terms of questions, if anyone has them, please type them in the chat, but I'll start off while we are awaiting questions from the audience. When you're looking at the measures from the XSense and those IMU devices, how do they actually compare for measuring, say, hip abduction or adduction, sorry, compared to something like a 3D motion analysis system with the validity and reliability of those measures?
Well, we had the previous studies published in Sensors, which did specifically this kind of comparison with Vicon 3D motion capture on actually the same cohort of subjects, and we found really a great correlation, great accuracy in all the specific joints that are involved in biomechanical analysis for anterior cruciate ligament injury. So if we deeply look into the specifics for joint angles that we consider, as you were saying, like hip adduction, internal external rotation, and new valgus, all these parameters are well captured by XSense.
Yes, and I think that's really important with wearable sensors, that we have that reliability and validity of them. In terms of your data, you collected on both sides, correct? The athletes doing both movements from both sides. Did you notice any side-to-side differences in outcomes of dominant, non-dominant side?
Yeah, dominant, non-dominance was one of the parameters that we put in our multi-homologous regression, but contrary to what we expected, there was no influence of the dominant side to these biomechanical risk patterns. And actually, literature is still divided on this, since there is no effective association with the dominant limb for anterior cruciate ligament injury proved and stated to now.
Great, thank you. We've got a question just come through from Daniel. how is internal and external rotation in the measured in the ankle, and what landmarks were used?
In the ankle, you mean? Well, we have sensor placed on tibial shin and on the foot, and this was internal calibration of the sensor. So the biomechanical model below the axis did this yes, internal external rotation angle.
Okay, so the foot could be turning out on its own, going into, say, eversion, inversion, without the tibia actually moving. So do you think that could be a limitation of that measure potentially?
Well, let's say that the system is designed in a way that you cannot distinguish between the age of the malleoli or the epicondyle, so that might be little issues in the analysis of internal external rotation, either for the knee or for the ankle, and this is also what we found in our previous study. But there's a good level of approximation for an analysis that comprehends multiple joints.
Okay, thank you for that. Is there any other questions from anyone? If not, I think we're just finishing on time for the session, so that's great. I'd like to just conclude by thanking our 5 speakers. So Lorenzo, Rhiannon, Guido, Stefano, and Jasper. Thank you guys so much for your talks. If anyone does have any questions as follow-up for our speakers, then please, I'm sure they'll be more than happy to take them either in some of the social events or potentially just send them an email as well. Thank you everyone again for your time, and we'll see you in the next session shortly. Bye everyone.
Thanks again.
Thank you guys. It's a great job.
Thank you. Thank you. Bye. See ya.
I'll just stop the recording here now as well.